Okay, welcome everyone to this continuation of what is algebraic geometry. Today I would like to tell you again about the differentials. Because why do we even define differentials? Well, you define differentials because differentials actually give you the way to compute the tangent. This is the most horrible tangent ever. So let me try again. I could actually just use whatever. I could make it really linear if I want to, but I guess you know what a tangent is. So what you really want to define with a differential, right? That's the whole point of differentials, is a tangent, and you collect them all in a bundle, in a tangent bundle, in a tangent sheaf. So those things go under various names, sometimes tangent bundle, sometimes tangent sheaf. I feel like, well, it will be a sheaf, but I feel like the tangent bundle is the more well-known name, so I just go with it. But you can call it the tangent sheaf, as I said, and it will be a sheaf, essentially by construction or by some lemmas that I didn't want to do. But anyway, we'll see. So the main idea, as usual, is a tangent bundle. So a vector bundle is you associate a vector space to each point, which is really just a linear algebra way of defining a cylinder if you want. So at each point you have a vector space. And for a tangent bundle, you kind of want to do the same, but at each point you want to have the tangent space to a certain type of manifold or variety in the setting of algebraic geometry. Namely, you want it to be smooth or something. But it's essentially the same idea, just we associate to every point now a tangent. That's what we want. And remember that tangent, well, a vector bundle, that's essentially the same as a sheaf of modules. Just somehow a different type of construction from a different field. That sounds a bit strange. Kind of a similar type of constructions, just from a different field. That sounds much better. Kind of doing the same thing. And yeah, tangent bundle and the tangent sheaf, they're kind of the same. They would kind of want to do the same thing. They just come from different perspectives. But it's like this idea of associating a sheaf of tangents to a reasonably enough space. And for a smooth space, it will do the correct thing. We can still do it for a non-smooth space. Whether it is a correct notion on a non-smooth space is a very different question, which I'm not going to address. But you can do it, and I tell you actually how to do it today in this video. That's the whole point of this video, right? This the second part of differentials. Remember the last times we had the differentials, and I didn't really give you an example. So here's the one example you should keep in mind, and everything is somewhat a generalization of that example, right? So that last time I tried to motivate it on polynomials. Well, and the polynomials is really just a coordinating of the affine plane. And then the affine plane is just a algebraic geometer's way of saying the plane, because geometers want to be fancy and they just call it the affine plane. It's really just R2 or C2, I guess, because I'm using complex coefficients. But let's not be too picky whether it's C or R. It doesn't really make a huge difference anyway. And the space of differentials, in this case, is like really easy. You only have derivative by x and derivative by y, because of course you just have a polynomial ring, and everything is determined from there on, and they also don't satisfy any relation. So essentially the space is just a direct sum of those guys, and the rest is just kind of making it, right? You can only take a derivative by the x or by y, and everything higher is you can kind of get it from those. So this is kind of easy to see that for the affine plane, the differential space is really just this beast here. Right? That's a good example to keep in mind. And then something you can do explicitly on this example, and well, we are doing algebraic geometry, so everything is polynomials. Everything is some form of a generalization of polynomials. So if we understand this example, we kind of understand everything. That's at least true in hindsight. It's maybe not true if you're really developing the theory, but in hindsight I think it's true. So if you already have the theory, you should always double check it against polynomials, right? That's what algebraic geometers do. And the way to double check it against polynomials is the following idea. We'll do that on the next slide, but first I need you to have a definition. So a bimodule, I think of a module as follows. So if you never thought a module, I think of a module as a line. So here my module is M, and whatever the acting ring, the acting algebra is A. And I think of a module as a line, and you can throw a ball as a wall, and you can throw a ball to it. Right? Some elements might go through the wall because it's kind of whatever, it's kind of whatever dashed. But essentially, it's just a wall, and you can throw a ball from it from left or right. Left module, right module. And a bimodule is something where you can throw a ball to it from both sides. We have an action from both sides. And a standard example of a bimodule is something like a tensor product, whatever R, tensor over something. Well, let's make it over the ground field. So R, and it is really just saying this funny symbol is really just this picture here, where you can throw an R ball. So that this would be R essentially. You throw an R ball from the right, you throw an R ball from the left, but something passes through, and these are exactly the scalars. So whatever you write on the tensor product is what can pass from left to right. So it's a little bit like not really a solid wall, but has a little bit of holes, and the thing that passes through is what you write on the tensor product. So the tensor product of this form is like the standard example of a bimodule. Really just this picture up here, right? So whatever goes through the wall, you write it down on the tensor product, and otherwise you can throw balls from left and from right. So we take this bimodule, and there's an obvious multiplication map. Well, maybe not obvious, but there is a multiplication map on this bimodule, which really just takes, well, the tensor product and multiplies it together. And this multiplication map is kind of the important one to really kind of give a alternative definition of the set of differentials, right? It's kind of an easy idea. You have this bimodule, or this prototypical example of a bimodule, this guy here, where scalars can pass from left to right, and you have a multiplication map on this thing down to, well, the same type of object. So it's kind of this type of multiplication map. So if you want to draw a picture, it would be something like this, where I'm not going to dotted one, but this is essentially what is M in the picture, and now you can multiply together and you get another element from M. It's like a little merge type object. And these types of things appear very, very often, and particularly they appear here as follows. So what you can actually do is the set of differentials, you can obtain it as essentially the kernel of the multiplication map. So more precisely, the kernel mod the square of the kernel is the alternative description of the set of differentials. And you can just do it explicitly for our affine plane here, because for our affine plane, what is the kernel of that map? Well, the kernel of that map are things of this form: 1 tensor x. So everything that kind of commutes is in the kernel, right? Because you multiply them together, and after multiplication they're different, they're the same, but before multiplication 1 tensor x and x on the 1 are not the same. And you can just easily check in this example that these guys span the space, and the isomorphism is given by sending dx to this thing, where you do action on the left, action on the right, and dy to this thing, action on the left, action on the right. And I realized now that this is actually the right and this is actually the left. So let me try again. Action on the right, action on the left. Not really a change, because left and right are of course interchangeable, but anyway, it was wrong. Anyway, so left and right difficult to distinguish. So, and this is an alternative description of this set of differentials, really given by expressing a differential as a multiplication operation in this bimodule space. And then you can define, for a variety, you can play exactly the same trick, and you can define a cotangent bundle as the corresponding sheaf of ideals associated to this quotient map. And I haven't really defined what a sheaf of ideals is, but you can literally just do it. So this isn't kind of an ideal description, because the kernel is ideal and the kernel squared is an ideal. So this is an ideal description, and there's a straightforward way of associating to an ideal a sheaf, and the pullback of that thing according to the diagonal embedding is what people call the cotangent bundle. It's not the tangent bundle, it's a dual of it. So the dual of that thing is the tangent bundle. And if you really, that's kind of the abstract definition that works for every variety. It just uses this idea of having those ideals around. And if you really do the calculation, like explicitly for something nice, like projective space, so this is not completely trivial to compute for a complicated variety. Complicated varieties are complicated. But if you do it for something easy like projective space, you end up with a picture you want to end up. So projective space is just a circle. The tangent on the circle is like this picture here, but it's kind of better to think of them as all separated. You just pull them all up into space, and it's essentially then an infinite type of cylinder. It's not finite because every tangent is an infinite line, so it's an infinite cylinder on the circle. And this just follows this is the abstract definition, and if you do it by hand, it's kind of magic. If you do it then in coordinates on the reasonable spaces, you get exactly what you expect as a tangent bundle. And the whole magic of this definition is this kind of a generalization to an arbitrary variety, essentially. With the slight catch that you actually get what people call the cotangent bundle, but it doesn't really matter all that much. Anyway, I hope you enjoyed this video, and I also hope to see you next time.